Okay, so very quickly, we have our due now on slide 19 of our digital notebook. And we have four examples, four different body diagrams, okay? Now, the net force is just the addition of all the forces acting on each other. So as you can see, we have a lot of vectors, and we know they're vectors because they're arrows with magnitude and direction. So the first one, what is the net force? The net force is just adding them together. So 5 plus 10, they're both facing the same direction. So 5 plus 10 equals 15 to the right, because they're all facing to the right. So 15 to the right, or you can just put positive 15. That's kind of the same thing. Now, anything that has a net force is considered an unbalanced force. That means if there's a net force, that means if there's unequal or unevenness, that means it is considered an unbalanced force. Okay? Same thing on the second example. We have 5 plus negative 10. The reason it's negative 10 is because now the arrow is facing the other way. So what do? Let's add them up. 5 plus negative 10 will give us 5 to the left, or just negative 5. That negative is telling us that's going the opposite direction. Okay? And the reason we know it's unbalanced is also an unbalanced force. The reason we know it's unbalanced is because there is a net force. If the net force is anything but 0, it's considered an unbalanced force. So as long as there is a net force, it's going to be considered unbalanced because it's not equal. It's uneven. It's very, very uneven. Okay? Even if it's a negative, yes. Whether it's a negative or a positive, it's still considered a net force. So it's considered an unbalanced force. Okay? Now, the next one right here, we have a 600 newtons facing north, and we have 800 newtons facing south or facing down. Now, we do the same thing. Since the 800 newtons is facing down, it's actually facing the opposite direction. So we're actually taking 600 newtons plus negative 800 newtons, which will equal to negative 200 newtons, or also known as 200 newtons down. That one's also giving us direction, okay? So the bigger value was 800 newtons, and that means that gravity is pushing it much more down than up. So the remaining force, the net force, was negative 200 newtons. Once again, this is also an unbalanced force because there is a net force. Now let's look at the last one. The last one's actually a different example. As you can see, that last one, it has 2 newtons of force on both sides of the up and bottom, and they're both pulling away from each other. Think of it as a tug of war. If I have one person pulling one way and another person pulling the other way, and they both have the same amount of force, we're not going anywhere. It's going to stay the same. So my 5 newtons are the same force, so they cancel out. And my 2 newtons are the same force, and they too cancel out. So in this case, my net force equals 0 newtons. So in this one is considered a balanced force because there is no net force. And yes, the 800 is negative because it's going down. Remember what we learned with vectors? If it's going down or going left, it's considered negative. If it's going right or going up, it's considered positive. So it's negative 800 because it's facing down. Okay? And since this is balanced, it has 0 newtons of net force. It's balanced because all the sides are equal. They're balanced each other. Yeah, so pretend, oh, great, yeah, great one. Yes, Emily. Yes, pretend it's a math graph. Yeah. In the math graph, you're moving to the right, it's positive. If you're moving up, it's positive. If you're moving down or moving left, it's negative. Yeah, exactly as a math graph. Where were you like 5 periods ago? I could have used your help. So we're officially on slide 20 for our notes. Remember, we have this right here text box where you can type in your answers as the notes as we follow along. If you have any questions, just put in the chat box and I'll answer them accordingly. Okay, so let's get started. Okay, slide 20 for notes. Now, last week, we talked about Newton's laws of motion, right? The first law of motion, an object in motion or an object at rest will stay like that unless acted by an unbalanced force. The second law of motion, force equals mass times acceleration. The third law of motion, a reaction has an equal and opposite reaction. Okay? Now, we did talk about force, not the forces in Star Wars, even though they are pretty similar. A force is an imaginary energy source. It's basically a push or a pull from an object. So, force is a push or a pull from an object. In this case, we're going to talk about two main categories of forces. We have unbalanced force and balanced force. Now, unbalanced force is exactly how it sounds like. It's the magnitude of forces that are unequal. That means they do have a net force. And net force just means the additions and the magnitude of these forces. Okay? So it's unbalanced if one side is heavier than the other, or if another side is greater or less than the other. So that's one unbalanced force. Think of it as a seesaw. Seesaw is very unbalanced. Okay? Then we have a balanced force. Okay? Balanced force is the opposite, is magnitude of the forces are equal. This one does not have a net force. That means all sides are equal. All sides are the same. They're balanced out. So think of it as a seesaw perfectly in the middle, or as a scale with equal weight on both sides. So balance means that they're equal on all sides. Okay. Now, balanced forces has two kinds of balanced forces, two kinds of them. There is static equilibrium and there's dynamic equilibrium. Static equilibrium means the object is at rest. If the object is at rest, that means it's not moving. That means all sides acting on it are equal. Okay, so take, for example, a book on a table, or a car parked, or you sitting down or laying in your bed right now. You're at rest. So that means all sides of the forces are equal. They're balanced. So this is considered, static equilibrium. Okay. Now we have dynamic equilibrium. The dynamic equilibrium is when the object is moving at constant speed and is not accelerating. That means it's not speeding up. It is not slowing down. It's moving at a constant speed. Think of it for any of my drivers. You guys, most of you guys are sophomore and juniors, which I'm pretty sure you guys know how to drive at this point, maybe. There's cruise control. Most cars have cruise control. If you click on cruise control, whatever speed you're at, it will stay like that. So if it's 25 miles per hour, it will stay at 25 miles per hour. And that means it's not speeding up, it's not slowing down, it's constant. So that's another example of dynamic equilibrium. Just it's going, but it's going at a constant pace. Okay. And then we have four types of forces that we're going to be talking about and focusing in the Newton's laws of motions. I have a 50-kilogram object right here in the center, and there's four arrows where the forces are acting on it. The first one is the arrow facing up, the force facing up, and that is considered the normal force. The normal force is a force pushing up. Now, I don't know if you have wondered why gravity doesn't just keep pushing us down. We have gravity pushing us down. There's a reason why we can walk around, and there's a reason why we are not pushed to the floor, is because of that normal force. There's a normal force acting against the gravity, which makes us actually walk around and just, do our everyday to-day activities, okay? So normal force is a force pushing up. Now, obviously, the force pushing down is gravitational force. And that is literally gravity. Gravity that Earth has given us, that is gravitational force. Is the force pushing us down? Oh, what did I do? Sorry. Is the force pushing us down? Okay. Gravity pushes us down. Normal force pushes us up, and it keeps us from falling to the floor, or from staying on the floor. Okay. Now on the right, we have another force that is the applied force. And the applied force, the applied force is a force applied to an object by a person or another object. Okay, so whichever direction you apply that force, that's the direction it's going. Whether I'm pushing to the right, or I'm pulling back, or I'm throwing something in the air, apply force is whichever direction I'm using that force, whether it's pushing or pulling. Okay, so that's applied force. Would that be a balanced force? Yes. If the normal force and the gravitational force are equal, then yes, it's considered a balanced force. So right now, the reason that we can walk around, that's considered a balanced force because there's no force pushing us down or pushing us up. Good one. Very good one. And the last one we have is our frictional force. Every force has to have a counter force. So in this case, if I threw a ball, or if I kicked a soccer ball, the ball doesn't go on forever, right? It stops at a certain point. That the point that it stops, the reason it stops is because of the frictional force. Frictional force is the force that goes opposite of the applied force. So if I kick the soccer ball, eventually that soccer ball will stop because of the friction force trying to oppose it. Now, if there was no frictional force, if I threw a baseball or kick a soccer ball, that ball will go on forever. It will never stop because there's no force opposing it. So normal force and gravitational force oppose each other. Frictional force and applied force oppose each other as well. Okay. I'll give you a couple more seconds to copy that down. The instructions for slide 21 is I want you to label the following diagram with the proper forces. So whether it's normal, applied, gravitational, frictional, there's 4 yellow boxes that you can literally just type in your answers. I want you to label where each of these forces go, okay? Once you do that, there are 3 tables on the right. I want you to answer those questions. First of all, is this object balanced or unbalanced? Second of all, if it's balanced, is it considered a static or dynamic equilibrium? And the last one, what kind of net force is it? Is it 0 or is it a non-zero value? Awesome, thank you for those ones. So we know normal force is the force pushing up, gravitational force is the one pulling down, applied force and frictional force are opposite of each other. So is this object balanced or is it considered unbalanced? For the most part, I did get balanced, and that is indeed correct. Some of you guys second guess yourself. Don't second guess yourself. It is balanced because the 2 newtons of force are going opposite directions, so they're pulling away, but they're pulling away at the same force, so they cancel out. And then the frictional force and the applied force, they're both pushing at 5 newtons of force, but they're both pushing together, so they're not going to go anywhere. So both my sides, up and down, are balanced, and left and right are balanced. So this is considered a balanced force, okay? Now, since it's a balanced force, is it in static or is it in dynamic equilibrium? Since we know they're all equal, it's all balanced, look at this box, look at the image. Does this image suggest that it's moving, or does it suggest that the box is at rest? Does this image suggest that the box is moving or that the box is at rest? Remember, it's static if it's at rest, it's dynamic if it's moving. For the most part, it is considered static equilibrium because object is at rest. There's nothing telling me that the object is moving. There's no one pushing it. There's no one pulling it. There's no one dropping it. There's no one picking it up. Nothing here in this image suggests that it's moving. So by default, it's at rest. It's static equilibrium. Now, very quickly, if it's balanced, if everything is balanced, what is the net force? What is the value for the net force? If it's balanced, what is the net force? Indeed. Thank you, thank you, thank you. Indeed. Yeah, very simple. If everything is balanced, there is no net force, or you can put 0 newtons. There is no net force. Since everything is balanced, there's nothing trying to pull each other away. Nothing's trying to pull each other away. Nothing's trying to push each other towards something. It is balanced, so there's no net force. Now for slide 22, the arrows are still pointing the same direction, so we still know that this is normal force. We know the bottom one, if it's facing down, the arrow, it's considered gravitational force. And then we got applied force, and then the opposite one is always going to be frictional force. Okay. Now, the only difference between this one and the last one is that now we have different newtons of force. We got 2 newtons of force of frictional force, 2 newtons of normal force, 2 newtons of applied force, and then 5 newtons of gravitational force. So just by looking at this image and this image alone, just by looking at it, is this object balanced or is it unbalanced? Yes, this one literally is considered unbalanced. It's an unbalanced force. Unbalanced force. Because look, we've got frictional force and applied force. They're both pushing the box at 2 newtons of force. So it's not going to go anywhere. It's staying there. That sucker is staying there. However, the normal force is about 2 newtons facing up, but the gravitational force is 5 newtons facing down. So this is not equal. This is very uneven, unequal. So it's considered an unbalanced force. And since it's considered an unbalanced force, we don't have to put anything if it's static or dynamic equilibrium, because it's not in equilibrium, it's unbalanced. So we can't answer that question. The question we can answer, though, is what is the net force? We know it's not going to be 0 because it's not balanced, it's unbalanced. So what is the net force? Give me the value and give me the direction. What is the net force on this object? So we can all agree it is 3 as the number, right? Now, that's the thing we have to think about. We know the frictional force and the applied force cancel each other out. And we know we're trying to push 2 newtons of force up, and we're trying to pull 5 newtons of gravitational force down. So we always know the bigger value is 5, but we do have that too. So let's take that 2 newtons of force and let's add that to our -5 newtons. The reason it's -5 is because it's facing down. So what's 2 plus -5? Well, it is -3 newtons of force. Right? So you can put -3 newtons, or you can put 3 newtons down or south, whichever one you want to put. Okay. Okay. So 3 newtons force down or south. Because the stronger, you can even see on the vector, look at the arrow. The arrow is much bigger, much longer. So we know that the main force is going to go down, but by how much? Well, by about -3 or just 3 newtons facing down. Okay. Yes, very great question. It will be considered wrong if you don't include the units. So make sure you always include, from now on up until forever, make sure you include your units, okay? Very important. You rather have 5 pennies or $5. Those are also units, so.